Okay, 1.61. Two touching bars, 1 and 2, are placed on an inclined plane, forming an angle alpha with the horizontal. The masses of the bars are equal to m1 and m2, and the coefficients of friction between the inclined plane and these bars are equal to k1 and k2 respectively, with k1 greater than k2. Find the force of interaction of the bars in the process of motion and minimum value of the angle alpha at which the bar starts sliding down. This angle is alpha, this is m1, and we have m2. It's also mentioned the coefficient of friction here is k1 and here is k2. Okay. Now this one, we need to find the force of interaction between m1 and m2. So obviously m2 is pushing on m1, right? And because of Newton's third law, m1 will be pushing on m2. So we really have to look at each of these bodies separately as two separate systems to find that internal force. We cannot look at m1 and m2 together. Let's start with drawing the free body diagram for m1. Okay, so the Earth's pull m1g in the normal direction, the normal reaction n1, okay, and then there is the force of friction along the surface k n1. Why is it in this direction? Because the system is moving downward. And then on m1, m2 is exerting, let's say, a force of interaction F. Okay, and this entire system is moving with acceleration. Similarly, let's draw the free body diagram of m2. m2, the Earth's pull m2g. There is this normal reaction n2. There is this friction force k n1, n2. Okay. Now, since m2 exerts a force of interaction F on m1, m1 exerts a force of interaction F or minus F or F in the opposite direction on m2. Okay. Now, if we had considered m1 and m2 as one system, F would be the internal force, it will go away. But because we are considering m1 as a system and m2 as a separate system and drawing the free body diagram, that's when this internal forces show up. Now, the entire thing is also moving with acceleration A. So now that we have these, can we write down the equations of motion? So this angle is alpha, this angle is alpha. Okay, so n1 and the component m1g cos alpha, they cancel out because there is no movement in this normal direction. So in this direction, what are forces we have? We have F, we have the component of m1g in this direction and kn1. So F minus m1g sine alpha, mf plus m1g sine alpha minus kn1 is responsible for this acceleration. So m1a. Okay, now let's look at this one. n2 is mg cos alpha and m2g sine alpha in this direction minus F minus K N2 is responsible for this acceleration, which is M2A. Okay, now our goal is to find F, right? We have everything. So let us write this as F plus M1G sine alpha minus K M1G cos alpha is M1A. And this one we can write M2G sine alpha minus F minus K M2G cos alpha plus M2A. Okay, now A is unknown, so let's just eliminate A from both these equations. So this becomes F plus, we can take this common sine alpha minus K cos alpha divided by M1, which is A, and on this side M2G sine alpha minus K cos alpha minus F divided by M2 is A. So now we can equate these two. F Oh. Okay, so that is the force of interaction. Now the second part of the question is, what is the alpha at which, minimum alpha at which M1 and M2 start moving, right? So to consider the case when it starts moving, we can say when bodies we can say A equals 0. So we can substitute in this equation A equals 0. So what will happen? So F plus M1G sine alpha equals K1 M1. That is alpha. So F is M1 M2 K1 minus K2 cos alpha by M1 plus M2 G plus M1 sine alpha G equals K1 M1 cos alpha G. You can cancel out these G's. Cos alpha is linear to this on that side. So M1 sine alpha becomes, you cancel out M1 side. So this becomes sine alpha equals K1 minus M2 K1 minus K2 divided by M1 plus M2. This times cos alpha. Okay, simple like this, M1 plus M2. So K1 M1 plus K1 M2 minus K1 M2 plus K2 M2 times cos alpha. So K1 M1, wait, K1 M1 plus K1 M2 minus K1 M2 plus K2 K1 M2 1. This becomes K1 M1 plus K2 M2 plus by M1 plus M2. And let's bring sine the other side, so this becomes tan alpha. So alpha is tan inverse this. Okay. Now